Hi everyone, let us review what we have so far. We have introduced this building block operator, identity operator, an evaluation operator, differential operator, an integral operator. An important part of the interaction between these operators are like this: D of function times identity operator behaves like this. That's the product rule. So if you see something like this, you can rewrite the operator into this way. So that's kind of the way P passes this D is this way. It's product rule. Very unnatural. And fundamental theorem of calculus says that if you do the integral first and D differential later, it's identity operator. But if you do differential operator first and integral operator later, it's close to identity, but not exactly identity minus this evaluation operator. So here's a little picture I summarized, and I just thought it's neat. This is the numbers that you learn early stage of your life, and you learn about numbers and how they add and subtract, and in calculus you even learn how to add infinitely many numbers. And the functions, it's on top of it, built on top of it. There's number world. Functions behave as if these are not numbers, a functional notation, a function called the sine x and a function called ex. This is not the numbers. This is a different idea. Lives above these numbers. And in it, we have all these operators. And plus, we have one more interesting operator. If you have two functions, you may be able to consider the composition of two functions. This is not easily explained using these 5 operations. It's additional operation that come in to this level. So focusing on this structure of this operation is called the group theory in mathematics. And what we're looking at operators is built on top of this space of functions. So something that moves these functions around is called operator. We've seen in an identity operator, an evaluation operator, in differential operator, and integral operator. We've seen how they interact each other if we juxtapose. In there, that's the multiplication. Multiplication here is a composition of two operators in this world. So that's the basic lemmas for 2 or 2 more of the algebra of the symbol D and symbol integral A, symbol I, and symbol E alpha. So to pass to this algebra a little bit more, we have to understand something called linearity of these symbols. All right, here it is, the linearity of an operator. We've seen the D and integral and I, those operator. They behave just like numbers. We can add them together and we can multiply together, which is really the composition. So linearity really helps to do that algebra on the symbols. So here's the very definition of the linear operator. Operator L is called a linear if it operates on a function in the following way. The C1 and C2 are constants, and F and G are functions. So if you consider this type of combination, we call linear combination of two functions over constants. That's the term that describes this shape of a function. Then the result of this one, after you operate with L, is always the same as this following: C times LF plus C2 times LG. You can write down the operator that involves y squared or y to the third. You can easily verify that they are, and this is not always satisfied. Special property. Here in this video, we're not checking all the linearity of these operators, but I'm showing you some examples and claiming that this is a linear operator. L here is described not in terms of how it's acting, let me hide that, but in terms of those building blocks. X squared is the function, and we differentiate first and multiply that function x squared. That's what this operator is. And identity operator don't then do anything to that given function and just multiply sine x and add them together. That's this operator described without the bracket y in it. And I'm claiming this is linear. To prove this linear, you have to take this verbatim exactly like this. None of the C1 and C2 are specified, or a function f and g are specified. With this arbitrary condition, we have to show this condition here, left-hand side, through this definition, is equal to the right-hand side through that definition. So here we're not going through that checking procedure, and I hope we usually do this in class, so I'll leave it there. In this part, I'm describing this operator with this y in it. So if I have function, then what this will do is x squared times the derivative of that function. So we're doing the derivative first, and we're going through this identity operator, then multiply sine x later. So order of these operations that is described in this operator notation is very important. And the statement that you need to check with your instructor or in your class is that this operator D, differential operator, evaluation operator, and integral operator, they're all linear operators. Remember, this linearity of operator is described in terms of the property that how this one acts on the functions. But it also has the consequence to how these operators are behaving each other. We'll come back more to this one later, but here I happen to have this one prepared showing that this operator is not linear. You don't conclude that it's not linear just looking at the square here, and you conclude this one dealing with the very definition of a linear. This one does not satisfy the very property to be linear. For example, I'm going to play with these two functions, y1 and y2, both are x. And you can just go ahead and choose your own example pair of functions. That usually it'll pick up that statement that says it doesn't satisfy the linear property. So first I compute this one, L of y1 to r plus y2, where I'm taking c1 and c2, 1 and 1. I'm just focusing on this addition of two functions. This is supposed to be equal to ly1 plus ly2. I'm proving here that is not the case here. If you do this operation first inside, y1 plus y2, that's 2x. So that's the order of this operation. You compute this one inside first, then do this L operator later. So 2x squared will be 4x squared. But if you compute ly1 and ly2 separately, since y1 and y2 both are the same, ly1 will be y1 squared, so it's x squared, ly2, of course, x squared. So now if you compare these two things, sum of these two things will be 2 times x squared, while this one turns out to 4 times x squared. So these two things are not the same for this very special choice of function. You can go ahead and choose your own, and you can probably figure out this is the case here again. So we found one example for which this linearity property is not satisfied. So you conclude that this is not linear. But when you have to prove this is linear, these two, playing with just a couple of examples, never establish the property for all functions and all constants. So that's why you can't play with that example when you prove this linear. When you prove it's not linear, playing with one example will be sufficient.